Hi, my name is Mark, and I'm an electrical engineer. I work for Texas Instruments. You might know us for the calculators that you use, but we are also one of the largest semiconductor manufacturers in the world. In case you don't know, semiconductors are the devices inside of your electronics that make them work. My job with TI is an applications engineer. I primarily help our customers use our devices, answer questions about how they work, help them with their designs, and solve any problems that they might run into. Problem solving is my favorite part of the job. Often it's like solving puzzles. Something doesn't work correctly or has a behavior that is unexpected, and I have to figure out why, and then find solutions to correct that problem or behavior. Sometimes our customers come to me with a general need, and then I invent a solution that will satisfy that need using our devices. Through most of my career, I've specialized in electrical power supply design. A power supply is a device that converts electrical power from one form to another. The topic of this talk is going to be about converting electrical power from one form to another, and specifically, I'm going to focus on the importance and use of magnetic fields to do this. We will be looking at two important devices that use magnetic fields called transformers and inductors. Don't worry if this sounds complicated. I'm going to make it simple to understand. First, you should know that magnetic fields and electromagnetic radiation are so important that without it, our world would be unrecognizable to you. Electromagnetic radiation is what makes all broadcast systems work. Without it, there would be no TV, satellites, radio, cell networks, wireless networks, radar, GPS, or microwave ovens, just to name a small number of things that wouldn't exist. And without using electric and magnetic fields in devices, we would not have the same power grid, there would be no electric motors at all, no electronics, and cars would be all diesel powered. You could argue that our mastery of electric and magnetic fields is what has enabled our modern age. Imagine life today the same as it was in the mid 1800s. That's where we would be today without this technology. First, we'll talk about the power grid, which is the system that we use to distribute power from the power plants to our homes or factories. Power distribution across the world is based on alternating current called AC power. AC refers to voltage that is constantly changing over time, kind of like a pendulum swinging back and forth. The second problem that I will talk about is that our electronics do not run from AC power, they run from direct current called DC. This is a voltage that is a non-changing value. For instance, a AA alkaline battery or the battery in a car are both DC voltages. And we need to create the exact voltages that our electronics need to function. As we go through this, I'm going to use a little math, but even if you don't yet understand the mathematics, you will be able to understand the basic ideas. Before we go on, here is Ohm's Law. It is the most important equation in all of electrical engineering, named after Georg Simon Ohm, and is a very simple equation. It says that voltage equals current times resistance. Voltage is the push or force on the electrons. Current is the flow of electrons. Using algebra, we can change this around to solve for any of the three variables like this. So knowing any two of the three variables allows you to calculate the third. To help you understand Ohm's law, think of a water hose. The pressure in the hose is the same as voltage. The water is all of the electrons. The water flow is the same as current flow. The amount that the nozzle is turned on is the resistance. When the nozzle is turned on a little, that resists the flow of water and is a high resistance, so little water flows. When turned on more, it opens and has less resistance and more water flows. If we open the nozzle twice as big, the resistance is cut in half and the water flow doubles. This is exactly how electricity works with Ohm's law. Here's another equation called Giles Law, named after James Prescott Joule. It says that power equals volts times current and is measured in watts. You can think of power as heat. Now let's get on to the main topic, talking about the application of magnetic fields. Our power grid is the connection between the power plants and our homes or factories. We generate this power in a lot of different ways, including hydroelectric power, fossil fuel plants, nuclear power, wind generators, solar electric, and others. Since we have to send this power over long distances, we use a very high voltage, around 100,000 volts, which allows us to send more power using smaller wires. As the power gets closer to where we use it, our homes and factories, we need to reduce the voltage to something more reasonable. In our homes, we typically use 120 volts AC, a much lower voltage. Our grid starts at over 100,000 volts and ends up at 120 volts. As electricity moves from power plant to our home, we change to lower voltages using a very simple device called a transformer. It consists of two coils wound around something called a core, which is nothing more than a material that conducts magnetic flux. I've used some words here that you may not understand, so let's look at that and clarify. Back in 1831, Michael Faraday discovered that using what he knew about electromagnets, he could make a voltage appear on one coil by applying a voltage to another coil if they were both wrapped around a common magnetic material. This was the first transformer. So how does this work? There's a branch of physics called electromagnetic theory, which is the study of electric and magnetic fields. It is based on a set of equations called Maxwell's equations, developed by a man named Clerk Maxwell in 1862, and later refined by Oliver Heaviside in 1884. One of Maxwell's equations is called Faraday's Law of Induction, and it says that a voltage applied to a coil of wire causes a magnetic flux to flow and grow around a loop. Here is the equation. One of the things that you may not know is that Greek letters, both capital and lowercase, are used in science to represent specific things. In this case, the capital phi is used for flux, and the d/dt just means that flux is changing with time. This is called the differential equation, and you will learn a lot about that later in your high school or college math. But for now, just think of it as just meaning that flux is changing. To give you a physical picture, here's a coil of wire wound around a core that forms a closed loop. Applying a voltage to this coil causes flux to flow around the loop and increase as long as voltage is applied. Think of the flux as similar to water flowing around a circle. An interesting side note is that this business of flux was very controversial at the time. It was created mathematically to explain the phenomenon, but magnetic flux could not be seen directly, and many scientists thought it was ridiculous to name something that couldn't be observed. This is really a simple equation, and it has three terms just like Ohm's Law. In fact, one of the values is measured in volts, just like Ohm's Law. Rearranging this using algebra, we can show that E over N equals the change of flux with time. Now let's add another coil to this magnetic path like this. If we drive a voltage on one coil that has a certain number of turns, it creates a changing flux, which in turn causes a voltage to show up on the second coil. We can understand this by looking at the two equations. Because the two coils are wound on the same core, they see the exact same changing flux. Using algebra, we can rearrange these and equate them to show this. See the flux term in the middle? In effect, the magnetic flux couples the two windings and results in voltage transformation. Again, using algebra, we can show that the output voltage is equal to the ratio of the two turns of the two windings times the input voltage. So as an example, if we had 1,000 turns on the inside and 100 turns on the outside, we would get V out equals Vn over 10. So for a 100,000 volt input, we would get 10,000 volts out. This is exactly how a transformer works, and it is described by Faraday's Law. It's how we change one AC voltage into another. Now here is something that is very important. This only works for AC voltage and not DC. The reason is a practical reason, and I'll show you what the problem is. It can be shown that for a given physical core, the magnetic flux is proportional to the current flowing in the winding by this equation, where I is the current flowing through the loop, and the rest of the right-hand side are just physical constants. A is the cross-sectional area of the core, mu is a characteristic of the material of the core is made from, and L is the length of the path through the core. But all of these combined are just one number that is based on the physical construction, so the equation simplifies to this. Flux equals current times a constant. So the problem with DC is that it causes the flux to increase in the same direction forever, meaning that the flux approaches very high numbers. Using this equation, we can see that that very high flux is the same as very high current, which isn't practical. Therefore, DC transformers don't work, and because the AC voltage spends as much time negative as it does positive, it averages out to zero, and the flux is just changing direction all the time, so both flux and current stay around reasonable numbers in a transformer. Okay, we've talked about AC distribution of power and showed how a transformer works to enable the conversion of voltage from higher voltage to lower voltages. Without this technology, we would not be able to distribute electricity over very far distances at all. The next problem that we'll talk about is that we need to make low DC voltages needed by our electronics. This is what I've spent most of my career doing and is generally referred to as power supply design. We need to do this as efficiently as possible, meaning that we waste as little energy as possible. Wasted energy shows up as heat, so inefficient designs need to get rid of more heat. which makes the device hotter. Imagine what it would be like if your cell phone needed to have a fan to keep it cool, or if your computer generated enough heat to warm your room in the winter. Okay, that might be okay, but what about in the summer? That would not be okay. Our electronic devices use a low DC voltage. In the USA, we mostly use 120 volts AC in our homes, and our electronics run from voltages today mostly less than 3 volts. So we have to be able to use the AC power from our wall outlet and create the low voltages that we need for our electronics. It turns out that this is very easy to convert AC power into DC power using something called a rectifier. I'm not going to talk about that here, so let's just assume that we use a transformer to make a low AC voltage and rectify it to create a DC voltage that we now want to use to run our electronics. The problem now is that we need to make all of the voltages that we need from that one other voltage. Consider this simple block diagram as an example. We start with an input voltage, 12 volts in this case, and need to generate all of these voltages and currents indicated that our piece of electronics needs. This is the beginning of what I might have when I start to design a power system for one of my customers' products. There is a very easy way to change DC to a lower voltage called a linear regulator. You can think of a linear regulator as a device between the input and output that just limits the flow of current to make the output voltage be what you want. There are a lot of devices that do exactly this, but they have one significant problem. They can be very inefficient. Consider using a linear regulator to create our 5-volt output. Our load, which is the power that we need, is 5 volts times 0.1 amps equals half watt. Remember Giles Law. We can also calculate the power lost in the linear regulator by seeing that the voltage across the regulator is 7 volts, 12 volts minus 5 volts, and the current is the same 0.1 amps. The lost power is therefore 0.7 watts. The input power is 1.2 watts, 12 volts times 0.1 amps, and the efficiency, which is defined as output power divided by input power, is 42%, not very high. For this 5-volt application, you might decide this is okay because it isn't much power. But now consider the 1-volt rail. It would have an efficiency of 8.3%, meaning that to generate the 50 watts that the load needs, we would be wasting 550 watts. Clearly, this isn't okay. But all is not lost. We have Faraday's Law of Induction to save the day. I will now show you how we use something called an inductor to create an efficient power supply to convert our 12-volt input to 1 volt with high efficiency. So first, what is an inductor? At first glance, it looks similar to a transformer. It is a single coil wrapped around a magnetic core. One thing that we haven't talked about yet is that when we create a magnetic field, meaning when we make flux flow in the core, energy is stored, not wasted. Using Faraday's Law, and adding a bunch of the physical properties of the core and windings, this turns into an expression that describes the behavior of an electrical component called an inductor, and is voltage equals inductance times di dt. This should make intuitive sense since we have already shown that there is a direct relationship between flux and current. L is called the inductance. A way to think about this is that to make the current change in an inductor, you have to apply voltage to it for a period of time. Another thing to see is that if the voltage is 0, then there is nothing to cause the current to change one way or the other, and it continues to flow. It is this current stored in the inductor that equates to energy, and the energy is equal to 1/2 times inductance times the square of the current. I won't derive this here, so you'll just have to trust me. We can use the inductor's ability to store energy to make conversion efficiently. Unlike in our linear regulator example, where the current flowing through the device with the voltage across it dissipates heat, when voltage is across an inductor and current flows, the energy isn't lost, it's just stored for future use. To understand how this works, let's consider a flywheel analogy using this bike tire. The rotating tire is like the inductor. If I spin it, it will keep spinning until something slows it down. In this case, any friction in the system, but it will spin for a while before it stops. Think about the force that I apply to the pedal as the voltage. If I now add resistance to the tire to slow it down, that is the same as the load and is where the output power goes. To get a certain output power, the wheel needs to spin at a certain speed. If the wheel spins too fast, as it does if I apply my force to the pedal constantly, the output power is too high, which would be the same as the output voltage being too high. To regulate the output power to the desired level, what I can do is to apply my force in pulses. If I make the pulses more frequent or in a longer duration, the power goes up, and if I do the opposite, the power goes down. If we apply the same technique of pulsing the force or voltage to our power supply problem, we can regulate the output voltage without dissipating a lot of power. This is called a switching power supply and is more efficient. Let's look at how that works with our inductor. This is called a buck regulator, which is a circuit used to convert a smaller voltage from a larger one. When the upper switch is turned on, the voltage applied to the inductor is positive and the current rises. At some point, we turn off the upper switch and turn on the lower switch, and the voltage across the inductor is the opposite polarity, and the inductor current starts to fall. By controlling the time that the switches are on, we can control the current in the inductor. And if we do this so that the inductor current is exactly equal to what is needed by the load, then we are generating the correct output voltage. The control of this circuit is beyond the scope of this talk, but it is a circuit designed to monitor the output voltage and control the switching so that Vout is exactly what is desired. Now let's look at efficiency. The efficiency of this circuit is determined by the power lost in the components that are conducting current. The three devices conducting current are the two switches and the inductor. Since the inductor is a coil of wire, its resistance is just the resistance of the wire, and the switches can also have very low resistance. The resistive power loss can be made very small, and the efficiency can be made very high. Using inductors like this is exactly how we power the various ICs that are in all of the electronics that you use. Both the transformer and inductor use magnetic fields to operate in different ways. The transformer uses the magnetic field to couple two windings, and with a difference in the ratio of wraps around the core, we can change the voltage. The inductor uses the magnetic field to store energy, and in doing so, it allows us to convert from one DC voltage to another using switches that are very low, have a very low voltage drop across them, and therefore low power dissipation and high efficiency. This has just been one example of how science and mathematics has helped us have the quality of life that we have today. I love engineering, I love science, I love mathematics. It's important, it's interesting, it's fun, and hopefully you will see that and pursue that in your education. Thank you for listening.